Hello everyone, my name is Puya Rostami. This is our work with Dr. Izzadi and Dr. Haydar Nouri titled as Automated Recovery of Issue Commit Links Leveraging Both Textual and Non-Textual Data. To talk about these topics, first we need to know some basic information about issues and commits. Issues and commits are two software artifacts that is used in software developments. Issues usually encapsulate user discussion around different aspects of the software, and commits contain the code changes related to fixing a bug, adding a feature, or something like this. Issues are stored in bug tracking systems like Jira, and commits usually are stored in version control systems like GitHub. Developers should mention the name of the issue they are working on in their commit, but usually this is not the case because they are under deadline pressure or they have some kind of distraction that made them forget to do this. But what are the benefits of this connected issue and commits, or what we call it, this issue commit links? We can use these links to improve our bug prediction solutions, bug assignments, or other software maintenance tasks that plays an important role in our software development and in our software evolution. But to know how much of these issues are links to commits, in 2019, a study over 500,000 issues on GitHub shows that only 42% of these issues were linked to the corresponding commits. But how can we properly link these issues to the corresponding commits? This is what we are going to talk about more in this presentation. But in order to know a little about it, we need to have some features, and we need to have a model that learn from these features to connect these issues to the corresponding commits. Here we have an example of a connected issue and commit which we brought for you. If you look closely, you can see that there's lots of information related to this issue and commits which we can use. For textual data, we have a diff code and a commit message, and for textual data of issue, we have a header and we have the description of these issues. And for non-textual data, we have type, status, the dates related to those issues, the assignee and the reporter of issue. Or for commits, we have the author of the commit, committer, hash related to that commit, and the name of these changed files. Many studies use this textual data and try to using these in more sophisticated models to increase the performance, but we decided to focus on using non-textual data better and more in order to use simpler models and also increase the performance of our model. In this slide, we will go through some existing approaches for linking issue and commits since 2010. We have categorized these models into three main categories of heuristic-based, machine learning-based, and deep learning-based methods. FRLink was the first paper which we studied. FRLink was not really an automated method for connecting issue and commits. It was a suggestion tool that helped experts to connect these issue and commits. The next paper is MLink. MLink was the first one trying to do this connecting issue and commits automatically. To do this, they have come up with a layered model. In this model, each layer try to connect this issue and commits based on a specific feature, and if that layer is unable to do this, they will send this commit and issue to the next layer to find possible connectivity. The next paper is Polymod, which is the first model that consider one-to-many links for issue and commits. In reality, there are some issues that need to answered by several commits because they are bigger and larger than usual. Unfortunately, the precision and recall for this model was in case of one-to-many was low, so it wasn't a very good model to use. Around 2015, the first paper using classifiers, which was the model that used in machine learning methods, was published. FRLink was the first one in this category. They have used changes scribe to create a new commit message and use this new commit message as a another feature beside the feature that commit and issue usually have. And after that, another team come up with FRLink, and FRLink plan to use the complementary information to learn relevant data about issue and commits and add these as a new features beside the features that each commit and issue already have. The next model that the same team published in the same year of 2017 was FullVersion, and in FullVersion they tried to teach the classifier by using true links and unlabeled links instead of using true links and false link, which is the common content to do in order to teach these classifiers. The problem with this method was that they need higher true links than the usual. Since 2019, a study started using deep learning models for this automatic connectivity. The first work was DeepLink by Shai that introduced in 2019, and in this work they have used a knowledge-based graph, and they combine this with a deep learning model for finding the connection between issue and commits. And the other work is the DeepLink by Ruan that also published in 2019, and in this work they haven't used any knowledge-based graph, and what they have done is that they gave all the textual information to a deep learning model, and this model learned to predict the connection between issue and commit for them. We have decided to use the DeepLink by Ruan and FRLink, which is basically the baseline for the DeepLink as our baselines. Their implementation can be found in the writer's GitHub account. Now that we have covered the background studies, we can talk about the problem with existing approaches. The first problem is that the recall and precision in some of the studies not considering having same importance, and they tend to think that recall is more important because in the end some experts will check these connections again to make sure that these connections are correct. But we believe that precision and recall should be high at the same time, so we don't need these kind of persons, expert persons, to check them again and have the perfect autonomous model to do this job. The other problem is that some of the models only consider one-to-many links, but we believe that it is important to consider these links, and we want to cover one-to-one links and one-to-many links at the same time. Other problem is that usually deep learning models use high computational powers, and high computational powers needs spending more money in order to be able to use these methods and models. So we want to create a model that not only have a good precision and recall and performance, but to use lower computational powers than the latest works in this topic. And also using deep learning models will cause to have some black box approaches, and we wanted to have the models that you can easily understand, and you can change it at your need in different situations. Now let us see an overview of our approach. In first step, we crawl data from our bug tracking and version control systems and extract the issue and commits existing in these information. In the second step, for data preparation, we do some textual data preprocessing like stemming, removing stop words and things like this, and then we generate true links and false links for our next step. True links are the links that really exist and the commit and issues that really connected to each other, and false links are the commit and issues that are not related to each other, and we only use them in order to train our classifiers to find the real true links later for our model. In third step, after creating these true and false links, we do some feature engineering based on the textual and non-textual data that we use for models. And in fourth step, we train two separate models. One model concentrating only on textual data, and the second model concentrating only on non-textual data and features that we have. And finally, we hypertune a linear accumulator of these two separated model prediction to create the best model-based prediction on the existing data of each project. For dataset, we use 20Met, which published in 2020 MSR and contains 20 years of issue and commits of Mozilla and Apache projects. For personal use, we have extracted the information of 12 projects of Apache from this dataset, and also added the diff code related to the commits of these projects, because the original dataset doesn't contain the diff code related to these commits. And the preprocessing used for these textual data that exists in these projects was tokenizing, removing stop words, and stemming, which are the basic preprocessing for NLP data. And after that, we use TF-IDF to extract the features from our textual data to use for classifiers training. By using TF-IDF, we give a weight to each word based on their population in the whole data and their population in their specific message. We also have tested other embedding methods like word2vec and doc2vec, and it didn't perform as good as TF-IDF. So we ended up using TF-IDF for training our models. In this slide, you can see an overview of our textual method. As you can see, we have separated the code information from our plain text, and we also separated the issue information from our commit information. And for our issue, we decided to use issue summary and issue description information. For our commit, we decided to use message, name of changed files, and also the diff code related to that commit to extract the features from them. For feature extraction, as mentioned, we use TF-IDF. We use 3 separated TF-IDF models to extract these features, and we feed these features to our binary classifier model to train based on them. And in the end, we have return of a probability of the issue being related to a commit. To find the best features for a non-textual method, we decided to study different columns of our data to find the suitable ones for these models. First, we inspected the data set for strongly correlated columns, and we figured out that the reporter column and creator column related to issues are the same in more than 99% of situations, so we decided to omit the reporter column. Next, we check the histograms on the status and type column related to issues, because they are the categorical type of data, and we figure out that we can reduce this categorical data to main categories by studying these histograms. And we ended up reducing the status categories to 3 categories of open, closed, and resolved. And for type, we reduced it to task, new feature, and bug. And in the end, in order to use this categorical data the best way possible, we used one-hot encoding, and we separated this data into different columns, different Boolean columns, to have the best features for our models. In the end, the overall information that we use for features of our model in issue information is created and updated date related to that issue, creator key, status, and type of those issues. And for commit, we use author date, commit date, the author of commit, and the committer person who committed that information. For our non-textual model, we decided to use 2 separated models and combine them in order to increase the performance without introducing too much complication on the matter. As a data, for data, we use the non-textual information mentioned in last slide, and by feeding them to these models, we train them, and we use an ensemble module to combine the prediction of each of these models, and in the end we have a probability of an issue being related to a commit as an output of this overall module. From now on, we're going to talk about the performance of our model in different situations. In this slide, we're going to talk about the performance of different algorithms on our textual method. As you can see, we have tested 4 different algorithms which are decision tree, gradient boosting, logistic regression, and stochastic gradient descent. And as it can be seen, the decision tree works better than logistic regression and stochastic gradient descent, and gradient boosting has the best performance amongst these algorithms due to its nature of being built upon decision trees and our data having lots of different features to learn from. In this slide, we are going to talk about different model performances for non-textual method. As mentioned before, we decided to use the combination of 2 different models in order to increase the performance of our method to be used later in the whole model. As you can see here, we have the information of the performance of each algorithm separately, and we have the performance of them in combination with each other to show the difference it makes when you combine these two different algorithms to each other. For simple method or separated algorithms, you can see that gradient boosting, random forest, and XGBoost works better than naive Bayes and generalized linear, because mainly we have binary classification and a list of features. So we participated that the models or algorithms based on decision tree can perform better than other algorithms. And you can easily see that when you combine these two, you're going to reach better precision and F measure than you use them separately. And we have decided to see the different combination of these three models, and we ended up choosing the combination of gradient boosting and XGBoost in order to reach the best F measure possible for our non-textual data. In this slide, you can see the different ways for combining textual and non-textual methods for different projects. The final prediction is made by multiplying this weight in the non-textual method prediction plus 1 minus this weight in the textual method prediction. We choose the weight that creates best F measure for overall model in each project. The difference between these weights for different projects shows that each project acts different based on the data it has. Hence, this weight cannot be fixed. If you look at the F measure value presented in green line, you can see that in most cases the weight is more than 0.5 in order to have best F measure, which indicates that in non-textual data plays more important role. But there is a case of Ambari project which has weight of 0.4, which shows in cases with better textual data or method use textual data instead. Here you can see the performance of our proposed method hybrid linker versus two baselines, namely DeepLink and FRLink for each project and in case of overall. DeepLink is the latest work with its resources available to use, and FRLink is the work that DeepLink itself uses to compare its proposed method. First of all, hybrid linker reaches the precision of 90.14%, recall of 87.78%, and F measure of 88.88%. Next, it outperforms DeepLink and FRLink except for the recall of FRLink. This is because in FRLink they solely focus on recall maximization, which we believe will significantly decrease autonomously of their method. As for discussion, our proposed method requires fewer computational resources than the state-of-the-art models, while outperform them in F measure with less time needed. You can see the difference between the running time of different projects on our mentioned models and deep learning model in our paper, and also we cover the concern of generalization using the 5-fold cross-validation on our data. For our future work, we concentrate on 4 major goals. We will study the control system and issue tracking system to find new features for our use. We will investigate other architecture for classifiers to increase the performance, and we will eventually want to find a way to specify this combination of the weights automatically instead of doing it ourselves, and we going to increase the number of projects for a study so we can cover the generalizability of our proposed method better than before. Here in this slide you can find the references to all the works we have mentioned in our presentation. Thank you for your attention. If you have any question, you can get in touch with us using the emails mentioned in our paper.